Hello everyone, in this video I would like to talk about the basic concept of calculus. Instead of talking about those formula and questions, I would rather talk about what makes calculus possible. For that we need to look at a paradox that was proposed 2500 years ago by a mathematician named Zeno. The Zeno paradox is talking about there was a Greek hero named Achilles raising a tortoise. And obviously, Achilles is much more faster than the tortoise, and the tortoise have an advantage for this. For the racing, the tortoise is 100 meters ahead of Achilles, and both of them racing at constant velocity. And let me draw a line first, and let's say this is the Greek hero Achilles, and this is the tortoise. The starting point of Greek hero, we name it as A, and the starting point of tortoise, we name it as B. Achilles need to catch the tortoise. For that, he need to advance to the starting position of the tortoise first, which is the point B. So he run 100 meter and reach point B. For the time that he run 100 meter, the tortoise would reach another position, which is point C. And obviously, since the tortoise is much more slower, the AB is much more longer than BC. So we find something interesting from this. We find that when Achilles reached the previous position of tortoise, the tortoise will always advance further, which means Achilles can never catch a tortoise. Is that true? Obviously, that is not true because in reality, that Achilles would catch a tortoise maybe in 2 seconds. So something must be wrong about the Zeno paradox. And what is it? So the mistake is Zeno assumed that to complete infinite steps, you will require infinite time. And we need to prove that it is wrong, or we need to make that is wrong to let the Achilles can catch up the tortoise. So first, let us look at the problem again. What we find is, if the Achilles keep approaching the tortoise, theoretically, it will be infinitely close to tortoise. The distance between them will be infinitely small. So after infinite steps of this approaching process, the distance between the tortoise and Achilles would be infinitely close to 0. The difference between them can be smaller than any imaginable number. We can use 0 as the accurate result of this process. So mind that this is not an approximation. This is the precise value of this process. But this is only the precise value of this process. It may not be the exact value of these events, but obviously when the time is flowing, the motion is continuous. So which means in reality, the distance is able to be 0, and eventually it would be 0 at some time, at some point on time. So when the distance between the Achilles and the tortoise be 0, the time required to complete the exact step would be 0 too, which means if you sum up all of the time required for all of the steps, it must be a finite number because it became 0. So this is the basic concept of limit. By this concept, Achilles finally catch up the tortoise as reality. What we see is limit describes the exact value that the process is heading toward, which is the destination of the train. It is the result of the infinitely approaching process, but not the result of the exact events. And now furthermore, let us look at some other concept of limit. And before we start, I need to underline that as a board writing, infinite is only a process, or you can say it is a tendency. It is not a constant. It cannot be used in calculation. This is very important. And a function can approach a value from both sides, from left or from right, so we call it one-sided limit. And function of us know, you put in an x, it is like a factory, it gives off a y. And obviously the function approach from left, we call it left hand limit, from right we call it right hand limit. And this is a notation of left hand limit. And that's the notation of right hand limit, which is a negative notation and positive notation. The arrow mean approach, and now we draw the graph and we can see more obviously by this function. This function is y divided by x squared. Now look at the situation when x is approaching the 0, and when it is approaching from left, it is a left hand limit, and which is positive infinite, and from right it is a positive infinite too, because obviously you can see it is approaching the infinite all the way up. And this notation, what we found is left hand limit is equal to the right hand limit, and we say this is the limit of this function, which is positive infinite. And without the positive or negative sign, it is just the pure limit. And now let us discuss about the existence of limit. There's two situations that limit might not be exist. One situation is what we have looked previously, is the left hand limit is not equal to the right hand limit. And in this situation, the limit is not exist. And another situation is more simple, just one of them or both of them is not exist. Now as previously, let us look at this function. This function is 1 divided by x, and when you approach it from left, obviously it go all the way down, so it is negative infinite, and approaching from right go all the way up is positive infinite. And now finally, the most important concept in this chapter is how to determine the continuity of function. And now suppose we have a function fx, and uh, we need to determine the continuity at the value x0. How we determine it is if the limit of x approaching x0 is equal to the function with the exact value x0. So in the question, we determine does the limit of this function exist, and what is the value, and does this point exist for this function, and what's the value, and is there equal. So eventually, if this is true, and this function must be continuous at that point. And now let's just look at this differentiation, the second chapter in the calculus. Before starting, all of us know that a straight line have a gradient. It have a rate of change, y divided by x. But does the point have a gradient? The answer is no. But now we are gonna do something that seems like finding a gradient of a point. But don't be confused. We are not doing that. So first, drawing a graph first. And this a curve y equal fx. And now we have a point. We name it as x0. And the whole idea right here is we want to find the instantaneous rate of change of the function at this x0 point, at this certain point. We want to observe how the function grow at this x0 point. In other words, you can say what we are finding is the gradient of the tangent line at the certain point on the function. For this situation, it is the x0 point. So what we wanna do is we want to let x1 infinitely approach x0. We make it keep approaching it. And first we find the gradient of this straight line AB, which connect the point x1 and point x0 on the function. So for the delta y, what we are finding is the value of y at this x0 point and subtract the value of y at the x1 point, so this delta y. And now we are making the approaching process, which is using limit. And finally you get something like this. And this is the first rule of the differentiation. What we are finding is the gradient of the function at this point, at this x0 point. Now we are done. So let's say this limit is exists for this function, and the conclusion is this function is differentiable at this point, which makes it is continuous at this point. And this notation, we call this the value of the derivative, and this another more common notation. This is the most common notation using dy divided by df. But this is not dy. This just look like dy. And like what I'm writing right now is, if a function is differentiable at an exact point, it is continuous at that point. And I'm not writing how to prove it. But this is just so obvious, because you cannot determine in which direction you are approaching it. Like, where's the delta x? At left or at right? So if it is differentiable, which means it can be approached from both direction, and that is an exact value on the function too, since the point is exists. Now let us look at this geometrically, which is the geometrical interpretation of the derivative. What we are preferring is same as just now, drawing a graph and take this, take that. The only difference is now we suppose an angle named theta 1, and just as before we have A and B, this straight line AB connect the 2 points. And although it's kind of ugly, but the line down there is the tangent, up there is the line AB, and that point is theta 1 and that point is theta. The theta is the angle of derivative, which means it is the angle that formed by the tangent at the exact point of the function with the x-axis. Obviously, we are making that b keep approaching a. We want to make them the same point. But we can see that the gradient delta y divided by delta x is equal to the tangent theta 1. So conclusion, the value of derivative, which is this limit, is equal to the gradient at the of the function at the exact point, and equal to this b approaching a with the function tangent theta 1. And gradient is equal to the tangent of the angle of derivative and equal to the value of derivative. And this is the most important thing at here is the tangent of the angle of derivative is equal to the gradient of that at that point. And now the final stuff of calculus is the integral, or we say it is the integration. Integral is more often to be seen, and there's two types of integral: indefinite integral and definite integral. There's a lot of difference between them, but first look at the indefinite integral first. This is quite simple, the indefinite integral compared to another. It is just the inverse operation of differentiation, and that's all. And this is the notation of integral, a weird curve. And at the middle, write the function. At last, you write this dx. The x can be any variant. For the position of x right now, it means the variant you are doing the integration inside the function. And since this is the inverse operation, so now we use this dy by dx as example. So when you integrate this dy by dx, you will get the original function plus a constant c. This c is just a constant, it is not any variant. It can be a lot of stuff. And why do we need to add a constant back to it? Now let us look at a more clear example. So when you are differentiate a function, the function might have a constant, maybe be 1, 2, 3, 4, 5 or anything, any 2.994, 4 divided by 3, any stuff, any real number. But after you differentiate it, this constant will always be 0. And we are not discussing about it because we are not discussing about any formula and any proof, but just keep that in mind. That's why we need to add up a constant back inside. And last, the most complicated one throughout all basic concept is the definite integral. And draw a curve too, like before. And it's starting at A and close at B. And this AB is a closed interval. Alright, before discussing this integral, why don't we look at how we find the formula of circle, perimeter, area, and a lot that kind of stuff. Um, we are not talking about how to prove it, how to find it, but all of us know exactly. We find it by we increase the size of the polygon and make it increase and increase and increase and increase. Finally, the polygon seems like a circle because that is too much of side for a polygon. So we find that we can use something straight to substitute something curved. And why don't we use this at here? Now look at this graph again. As I say, this is a closed interval A to B. And what we do first is we separate this. We divided it to n small intervals. And we name those points. And A is obviously the x0 and B is obviously the xn. And there's x1, x2, x3, x4, x5. All of them form n small interval. And this is what we find, the delta xi is equal to the xi minus 1. What we are saying is, like, for example, the delta x1 is equal to the x1 minus x0, which is uh, the length of a small interval. And for all of these points, x0, x1, x2, if we draw a line up and connect the curve at the top, which is the function, and we will get n curved trapezium. And we name the area of each of the trapezium be A1, A2, A3. Like the delta x1 is delta A1. We just change this notation only. Delta x2 is delta A2. And now let us find How to calculate the area? By the formula of the rectangle, we use the base times the height. The height is this function fci. This ci is any point inside the small interval. Since the small interval is too small, it's gonna be very small, infinitely small at the end. So it can be any point inside this closed small interval. And the base is obviously the length of the interval, the small interval. And now I'm drawing it to make it more clearly. It's kind of ugly, but it just seems like this. And they're gonna be infinitely small. This is just a demonstration only. And now we name this whole area under the graph be the area A by this notation. And the whole area under the graph will be the sum of each area of the small interval. Now represent it by the formula we find just now. Now for more obviously we write it by the summation notation. And by the way, this is what the mathematician Riemann find many years ago. And since Riemann found it, so it is named as Riemann sum. And just as what I was doing at whole of the video, find the limit again. Just as I said, make the delta x extremely infinitely small, and this is called Riemann integral. Now, in the purpose to make it more simple, we let the greatest among all of these small interval delta x1, delta x2, delta x3 be named as front. So as prime is infinitely approach to 0, all of the other interval must be infinitely approach to 0, just as what I wrote. So now, finally, this is the final conclusion. The area under of the graph is this formula, this stuff. So now let us discuss about what is the central concept of this operation. The central concept is linear approximation, which is substitute a curve by straight line. Because when you have enough of straight line, when you have an infinitely large number of straight line, eventually it becomes like a curve. It seems like a curve. And now look back at this proving process. The first step, what I was doing is subdivide. And the second step is doing the linear approximation, which is the most important strategy among this proving process. Now, linear approximation, of course, we use this curved trapezium to do linear approximation. It's named as curved trapezium, but they are just trapezium with straight side. And third step is summation, sum together those area, and the final step is find the limit, just as what I was doing in this whole video.